Hello everyone, myself Shikha and welcome to my YouTube channel. Today in this video, I'm going to give you a brief introduction to simple linear regression models and I'm going to implement it from scratch in Python. So first, we'll look at what linear regression is, then some important aspects on basis of which we would be selecting our regression model for a particular given data set. Further, we will see how the gradient descent algorithm works in our linear regression model. And once a model is predicted, we'll learn to evaluate our regression model. And finally, we'll be implementing it on a given data set in Python and we'll be making predictions for the same. So let's get started. What is linear regression? Linear regression in statistics is one of the simplest and widely used algorithms in machine learning. This linear regression basically uses a linear approach, as the name suggests, to model the relationship between a dependent variable and one or more independent variables. So, what is dependent and independent variables? Let's have a look. So, let's consider x as our independent variable and y as our dependent variable. So these independent variables are nothing but the input values from our given data set, and dependent variables, that is the y values, are the ones which are going to be predicted on the basis of these given input values from our data set. So what linear regression basically does is it predicts a dependent variable values y based on the given independent variable values of x. Since there are many regression techniques to generate a model, such as linear regression, logistic regression, etc., regression techniques needs to be like deferred, or we need to consider some major aspects on the basis of which we would be selecting the which regression model would be suitable for our particular data set. So there are two aspects which I'm basically focusing on. That is the number of independent variables and the type of the relationship, or you can also say degree of relationship between the independent and dependent variables. So let's start with the first aspect, that is the number of independent variables in linear regression models. So in case of one independent variable, it is referred to as simple linear regression, where we would have only one input column and one output column which would be predicted on the basis of the given single input column. Whereas in case of multiple linear regression, we can have like more than one independent variables. So here the output variable would be predicted on the basis of multiple independent variables or multiple input values, you can say in simple language. So before generating a model, the next aspect which we need to understand is the degree of the relationship between both the attributes y and x, that is our independent and dependent variables. So, mathematically, correlation between two variables indicates how closely their relationship follows a straight line. Basically, it means how closely their relationship shows any linear trend. So we can see when r value is near to -1 and +1, the data points are showing a linear trend, right? And when we see here when r is 0, the data points doesn't show any literal linear trend between them. So let's see how this coefficient of correlation is calculated. So this correlation has extreme values of either -1 or +1, which indicates a perfectly linear relationship between x and y. And but when we see this correlation of data set when r value is 0, we see that the data points are scattered here, because of which there is an absence of linear relationship here. So generating linear models for such cases where r is near to 0 makes no sense, right? This model will not be reliable for like linear models. So for a given value of x here, if we see for a given value of x, there are many values of y, there is not a particular value of y, which means that linear models will not be applicable in cases where r is near to 0. Whereas when r value is near to +1 here, the data points are showing a linear trend, a positive linear trend. Why a positive linear trend? Since as x values are increasing here, the corresponding y values are also increasing, which means this is showing a linear positive trend, and linear models can be applicable on this range when r is like near to positive 1. Similarly, when r is near to negative 1, the data points are showing a negative linear trend. Since as x values are increasing here, the simultaneous or the corresponding y values, we can say, are decreasing here. So this means that linear models can also be applicable on such cases, whereas when data points are scattered here, we prefer using non-linear models, which is a different topic. So the mathematical formula for this coefficient of correlation, or R, is given by covariance of x comma y upon standard deviation of x into standard deviation of y. So this is the mathematical formula for coefficient of correlation, or the Pearson's coefficient. And here xi and yi are the actual values for the given data point, and x bar is nothing but the mean value. This is x bar, mean value of all the x values of a given data set, and y bar is the mean value of all the y values of a given data set. So what we do here is we calculate the difference. Suppose for this data point, I want to calculate the this difference between actual and mean value. So it would be calculated by this x value, xi minus x bar, and yi minus y bar. So substituting the simultaneous values, we can like retrieve the coefficient of relation value. So for this particular data set, R value would be closely to 0, since as we saw earlier that for a particular data point x, we have many values of y, which makes the data points scattered on the feature space, and for such cases, linear models are not applicable. Then let's take an example here for a data set, and let's see clearly what linear regression is and how it basically works. So this scatter plot below shows apparent correlation between x and y. As we see, these black dots are representing the scatter plot for our data set, and these data points are showing a positive linear trend here. So but there are like infinite number of lines that can fit in the scatter, right? Which one should we consider as the best fit line for our model, or the regression line? So that would be computed by using gradient descent method, or variance of gradient descent method, which is used to find the best fit model, which basically this gradient descent method uses partial derivatives on the parameters slope and intercept. Why slope and intercept? So every line in mathematics is represented by the equation y equals mx plus c. That m is nothing but the slope of the line, and intercept is the y-intercept, where this line cuts on the y-axis. So what this gradient descent method does is it finds the best fit model by calculating the partial derivatives on these parameters in such a way that minimizes the sum of squared errors. So this is the major thing here. It finds the line such that the sum of the squared errors for all the data points in this data set is the minimum for that particular line, and that particular line is considered as the best fit line for our model. So let's see in detail what this error is. What error basically is that the distance between the actual point and the point on the predicted line is the error in prediction. So what is this point? Suppose for a given point x, this is the actual value, and this is the prediction line for our model. So for a given data point x, this would be the actual value from the data set, and this would be the predicted value from our model. So the difference between the actual and the predicted value is nothing but the error in prediction. So what we do here is we just calculate the error in prediction for each and every data point here, like all the data points present in the data set, and then we calculate the sum of the square of these errors, which basically means the sum of squared errors here. So evaluation in regression, once our like regression model is formed, we need to evaluate our regression model. So evaluation metrics are a measure of how good our model performs and how well it approximates the relationship. So what does this mean? Evaluation metrics basically is useful to get the measure of good fit for a model. So the most common metrics for simple linear regression tasks are MSE, nothing but the mean squared error, MAE, that is the mean absolute error, and R squared, that is the coefficient of determination, which we would see one by one in detail further. So let's have a look. So we'll first see the mean squared error here. So mean squared error function in our model. There are three steps to calculate this mean squared error. So the difference between the actual and the predicted value first we find the difference between the actual y value and the predicted y value for a given point x. Then we square these differences and then we find the mean of the squares for every value in x. That is, we add up the squares for all the values and then we divide it by the number of data points. So this is how the mean squared error can be calculated easily. And next metric is the mean absolute error. So this is simply the average of the absolute difference between the target value and the value predicted by the model. So both these, this is not preferred in cases where outliers are prominent in your data set. Outliers are the values which are out of your regression model, or you can say out of the regression trend that your model follows. So both these metrics MSE and MAE, that is mean squared error and mean absolute error, can range from 0 to positive infinity. So as both of these measures can have like higher and higher values, it becomes harder for us to interpret like how well your model is performing. So basically, the third metric, which is used to determine the efficiency of your model, is the coefficient of determinant. So this coefficient of determinant is also known as R square, and it is sometimes referred to as the goodness of the fit. So this term goodness of fit, what it means? So it basically implies that the closer the points get to the line, that is the closer the actual points are to your predicted model line, the better the regression model is. Means the better is the you can say efficiency of your model. So, and this goodness of fit of our model is evaluated by the term coefficient of determinant, which is also denoted by R square here. And this R is nothing but the Pearson's coefficient, which we saw earlier, that is coefficient of correlation. So, the closer the value tends to 1, the better the model is. And the value of R square basically ranges from 0 to 1. That is, it can be ranging from 0 to 1 values. Further, the coefficient of determination is also determined by correlation coefficient, the whole square. So this R is nothing but the coefficient of correlation, and the formula is also similar, just squaring the whole term of coefficient of correlation. So, in coefficient of determinant, what we try to specify is the goodness of the fit of the model. First of all, before going into this, we need to know what are the types of errors for our regression model. So, there are basically two types of errors in our model, that is stochastic errors as well as deterministic errors here. So stochastic errors are nothing but the residual errors, and deterministic errors are also called as regression errors. So let us try to understand what are these types of errors from the given data set below. So for this value of x, so let's consider this value of x. So for this particular value of x, p1 is the actual y value and p2 is the predicted value since it falls on the prediction line. This is a prediction line for the data set. So p2 is the predicted y value and p1 is the actual y value. Well, and so the difference between P1 and P2, that is the actual and the predicted value, is nothing but the stochastic errors, or known as residual errors here. So this, the difference between actual and predicted value, is called as the stochastic errors. And since these errors are not defined by our model, it is also called as undefined noise, or undefined variance, you can say. Next comes the deterministic error, which is also known as regression errors. As the name suggests, this these errors are defined by the regression models, and these are also called as deterministic errors. So this is nothing but the difference between the predicted y value and the y bar. So y bar here is nothing but the mean of all the y values of your data set. So the difference between the predicted y value and the y bar is nothing but the deterministic or regression errors for your data set. And this is the sum of squared total errors. So it is basically the sum of regression as well as residual errors. So, a small overview on what these errors were. So, regression error is basically difference between the predicted value and the mean of y values, whereas stochastic or residual errors is the difference between the actual y value and the predicted y value for a given data point x. And sum of squared total errors is nothing but the sum of both the regression as well as residual errors values. So these errors are very important to judge the goodness of fit of the model and select the best fit line for the model having the least sum of squared total errors. So our regression model would be our the best fit line for our regression model would be the one having the least sum of squared total errors for our data set. So that model is the most fit where every data point lies on the line, that is SSE equals 0 for all data points. So what does it mean? It means that the regression model, the best fit regression model would be the one where this difference between the actual and the predicted value would be 0. That is SSE would get nullified, which is very rare case because it doesn't happens usually that you have your residual errors as 0, but we try it to like be nearly close to 0. So where differences between actual and predicted values get nullified, this regression values gets equal to the SST as specified here, that the regression value should be equal to SST, that it would be 1. And poor fit, in contrary to that, poor fit will mean that SSE would be large. That means that if the difference between the actual and the predicted value would be too large, then it would be a poor fit model for our data set, which means that SSR, that is the regression errors, and the sum of squared total errors would get equal to 0, and this residual errors would be like very large or closely to 1. So this regression or sum of squared total errors is called as R square, that is nothing but the coefficient of determination. That is, this regression error difference between the predicted and the mean y value would be nothing but your coefficient of determinant, which would be defining the goodness of fit for your model. So So this coefficient of determination helps us determines the best fit model by calculating like the errors or the variance for like each and every data point here on the line, and then selecting the line having the least errors amongst all the best fit line for our simple regression model. So just like the coefficient of determination, the adjusted coefficient of determination is used in case of multiple regression to determine how well a multiple regression equation fits the sample data. In the next video, have done the implementation of linear regression model in Python. So do check out, and link is in the description below. And thanks a lot for watching. this video. Feel free to share your reviews and issues, if any, in the comment section. And if you like this video, just do like it, share, and hit the bell icon to stay updated with the upcoming videos. Thanks a lot.